Right now, there's a spacecraft so far away that if you sent it a message, it wouldn't arrive until tomorrow. Not because of slow internet or technical problems. Because the message itself, traveling at the speed of light, the fastest speed physically possible in the universe, takes 24 hours just to get there. In November 2026, NASA's Voyager 1 will become the first human-made object to reach one light day from Earth. That's 16.1 billion miles. 25.9 billion kilometers. A distance so vast that light itself needs an entire day to cross it. And here's the wild part, Voyager 1 launched in 1977. It's been flying for nearly 50 years to reach this point. It left Earth when Star Wars first hit theaters, when cassette tapes were cutting-edge technology, when most of us weren't even born. And it's still out there, still transmitting, still pushing deeper into the darkness. This is the story of humanity's farthest ambassador, the tiny spacecraft carrying our voices into the cosmos. Before we dive deeper into this incredible journey, if you're into historic space missions like this and want to see more content about humanity's greatest achievements in space exploration, hit that subscribe button. And if you're enjoying this story, drop a like and let me know in the comments what you think about Voyager's mission. Do you think aliens will ever find it? I'd love to hear your thoughts. Alright, let's get into it. To understand what one light day means, we need to talk about scale. In our everyday lives, we measure distance in miles or kilometers. Inside the solar system, astronomers use astronomical units, or AUs. 1 AU is the distance from Earth to the Sun, about 93 million miles. Light, traveling at 186,000 miles per second, covers that distance in about 8 minutes. So we say the Sun is 8 light minutes away. Neptune, the farthest planet, is about 4 light-hours away. Even the most distant objects in our solar system, out in the Kuiper belt, are measured in light-hours or maybe a light day or two. But Voyager 1 is pushing past that threshold. As of late 2024, radio signals from Voyager take about 23.5 hours to reach Earth. By November 2026, that number will cross 24 hours. A full light day. That doesn't sound like much compared to the vastness of space. After all, the nearest star, Proxima Centauri, is over 4 light-years away. That's more than 1,400 light days. Voyager has barely scratched the surface of interstellar distance. But here's the thing, Voyager 1 is the first. It's the pioneer. No human-made object has ever been this far. And the fact that it's still working, still communicating, still sending data after nearly half a century of continuous operation is nothing short of miraculous. Voyager 1's journey began on September 5, 1977. It was part of a rare planetary alignment that occurs only once every 176 years, allowing a single spacecraft to visit multiple outer planets using gravity assists. Voyager 1's primary mission was to study Jupiter and Saturn up close, and it succeeded spectacularly. In 1979, it flew past Jupiter, capturing stunning images of the planet's swirling clouds and discovering active volcanoes on its moon Io. In 1980, it visited Saturn, photographing the planet's iconic rings in unprecedented detail and revealing the complex structure of Titan's thick atmosphere. After Saturn, Voyager 1's trajectory took it above the plane of the solar system, heading outward at about 38,000 miles per hour. It wasn't done exploring. It was just getting started. By 1990, Voyager 1 was already 3.7 billion miles from Earth when Carl Sagan convinced NASA to turn its camera around one last time to photograph the planets it had left behind. The result was the famous pale blue dot image, showing Earth as a tiny speck suspended in a sunbeam. Sagan's reflection on that image became one of the most profound statements ever made about our place in the universe. After that, the cameras were shut off to conserve power. But Voyager kept flying. In August 2012, Voyager 1 crossed the heliopause, the boundary where the Sun's influence ends and interstellar space begins. It was a historic moment, the first time a spacecraft had left the solar system's protective bubble and entered the space between stars. Since then, Voyager has been sampling the interstellar medium, the thin plasma that fills the space between star systems. And it's still sending that data back, one photon at a time, across billions of miles of empty space. But maintaining contact with Voyager 1 at this distance is incredibly challenging. First, there's the signal delay. When engineers at NASA's Jet Propulsion Laboratory send a command to Voyager, it takes a full day for that signal to arrive. Then it takes another full day for the spacecraft's response to come back. That's a 2-day round trip for every communication. Imagine trying to troubleshoot a computer problem, but every time you type a command, you have to wait 48 hours to see if it worked. That's the reality for Voyager's mission controllers. They can't make quick adjustments or respond to unexpected behavior in real time. Everything has to be planned meticulously, with every possible scenario anticipated days or weeks in advance. One wrong command could end the mission, and there's no way to fix it quickly. Then there's the signal strength. Voyager 1 transmits at just 23 watts, about the power of a refrigerator light bulb. By the time that signal reaches Earth, it's unimaginably weak, less than a billionth of a watt. NASA's Deep Space Network, a collection of massive radio antennas in California, Spain, and Australia, listens for Voyager's faint whisper. These dishes, some as large as 230 feet across, are so sensitive they could detect a cell phone signal from Mars. But even they struggle to hear Voyager as it drifts farther away. And then there's the power problem. Voyager 1 doesn't use solar panels. This far from the sun, sunlight is far too weak to be useful. Instead, it's powered by 3 radioisotope thermoelectric generators, or RTGs. These devices convert heat from decaying plutonium-238 into electricity. When Voyager launched, its RTGs produced about 470 watts of power. Today, after nearly 50 years of continuous operation, they produce only about 220 watts. And that number drops by roughly 4 watts every year as the plutonium decays. NASA has had to make hard choices about what to keep running and what to shut down. Over the years, they've turned off the cameras, heaters, and several scientific instruments to stretch the remaining power as far as possible. Right now, Voyager 1 still has 4 active instruments: the plasma wave subsystem, the magnetometer, the cosmic ray detector, and the low-energy charged particle instrument. These are the most scientifically valuable sensors for studying interstellar space. But eventually, the power will run out. Most estimates suggest that some form of contact will be possible until the early 2030s, maybe 2032 or 2033. After that, there won't be enough electricity to power the communication system, and Voyager will go silent. It won't stop flying. It'll just stop talking. Even as its power fades, Voyager 1 continues to do groundbreaking science. The plasma wave subsystem detects oscillations in the interstellar plasma surrounding the spacecraft. By measuring the frequency and intensity of these waves, scientists can determine the density and temperature of the medium Voyager is traveling through. These measurements have revealed that interstellar space isn't empty. It's filled with a thin soup of ionized particles, remnants of ancient supernovas and stellar winds. Understanding this environment helps scientists model how our solar system interacts with the galaxy. The magnetometer maps the strength and direction of magnetic fields in interstellar space. These fields are thought to play a crucial role in shaping the galaxy's structure and channeling cosmic rays. Voyager's data provides rare direct measurements of these fields, offering clues about how our galaxy is organized on large scales. The cosmic ray detector measures high-energy particles streaming through space. Inside the solar system, the sun's magnetic field deflects many of these particles, creating a partially shielded environment. But in interstellar space, Voyager sees cosmic rays at their full intensity, providing a baseline measurement of the radiation environment beyond the sun's protection. This data is critical for planning future interstellar missions. Any spacecraft or crew venturing into deep space will need to survive this radiation, and Voyager is giving us the first real-world measurements of what that environment looks like. Voyager also carries something even more enduring than its instruments, the golden record. Mounted on the side of the spacecraft is a 12-inch gold-plated copper disc containing sounds and images from Earth. It includes greetings in 55 languages, music from around the world, ranging from Beethoven to Chuck Berry, and 116 images showing life on Earth. The record also contains natural sounds, thunder, wind, ocean waves, birdsong, and even a human heartbeat. There are greetings from world leaders, including then-President Jimmy Carter and UN Secretary-General Kurt Waldheim. Carl Sagan, who chaired the committee that created the record, called it a message in a bottle cast into the cosmic ocean. The odds of it ever being found by an extraterrestrial civilization are vanishingly small. But even if no one ever listens to it, the golden record serves as a time capsule of humanity in the late 20th century. And it's now more than a light day away from home, drifting farther into the darkness with every passing second. Voyager 1 isn't alone out there. Its twin, Voyager 2, launched 2 weeks earlier in August 1977, is also in interstellar space. Voyager 2 took a different route, visiting Uranus and Neptune before heading outward. It crossed the heliopause in November 2018, becoming the second spacecraft to enter interstellar space. Both spacecraft are still operational, still transmitting, still doing science. It's an extraordinary achievement, a testament to the skill of the engineers who designed them and the mission teams who have kept them running for nearly 5 decades. But their journeys are far from over. Voyager 1 is currently traveling at about 38,000 miles per hour relative to the Sun. That sounds fast, and it is by human standards. But on cosmic scales, it's incredibly slow. At this speed, it will take Voyager about 300 years to reach the inner edge of the Oort cloud, the vast shell of icy body surrounding the solar system. It will take another 30,000 years to pass through the Oort cloud entirely. In about 40,000 years, Voyager 1 will make a close approach to a star called AC plus 793888, passing within about 1.6 light-years of it. Of course, close approach is relative. That's still trillions of miles away. And by then, Voyager will have been silent for tens of thousands of years. Eventually, millions or billions of years from now, Voyager may drift into another star system. If an intelligent civilization finds it, the golden record will be there, a greeting from a species that existed long ago on a small blue world orbiting an ordinary yellow star. Or it may drift through the galaxy forever, a silent emissary of a civilization that rose and fell on a distant planet, its message never heard. The approach to one light day is more than just a number. It's a reminder of what we're capable of when we push the boundaries of exploration. Voyager was built with 1970s technology. Its computers have less processing power than a modern calculator. Its data storage is measured in kilobytes. It communicates using technology that would seem ancient today. And yet, it works. It's been working continuously for nearly 50 years, exposed to radiation, micrometeoroid impacts, and the extreme cold of deep space. It survived far longer than anyone expected, and it's still sending valuable data. The lessons from Voyager are shaping the design of future interstellar missions. Engineers are studying how its components have aged, how its power systems have degraded, and how its communication systems have adapted to increasing distance. Future probes will need better power sources, perhaps nuclear reactors or advanced solar sails. They'll need more autonomous navigation systems, capable of making decisions without waiting days for instructions from Earth. They'll need to be tougher, more resilient, able to survive journeys that may last centuries. Voyager is teaching us how to build spacecraft for the long haul. There's also something deeply human about Voyager's journey. It's not just a machine. It's a reflection of who we are, what we value, and what we dream about. When Voyager launched, the Cold War was at its height. The world was divided, tense, uncertain. And yet, NASA sent a spacecraft carrying a message of peace and curiosity into the cosmos. The golden record doesn't talk about war or conflict. It talks about music, art, love, and the beauty of our planet. It's a hopeful message, sent at a time when hope was hard to find. And now, nearly 50 years later, that message is a full light day away and still moving. Voyager 1 will keep drifting outward long after we're gone. It will outlast nations, civilizations, possibly even the human species itself. In some distant future, when Earth is no longer habitable and humanity has either spread to the stars or faded into history, Voyager will still be out there, carrying our voices into the void. The One Light Day milestone in 2026 is just a marker, a moment to reflect on how far we've come and how far we still have to go. Because even after 50 years of travel, Voyager has barely left home. The nearest star is still 4 light-years away. The Milky Way is 100,000 light-years across. The observable universe is 93 billion light-years in diameter. Voyager's journey, as epic as it is just the tiniest step into an incomprehensibly vast cosmos. But it's our step. And that matters. So here's to Voyager 1. A machine built by humans, powered by human ingenuity, carrying human voices into the endless dark. A spacecraft that reminds us that we are explorers, dreamers, and builders. And even when it falls silent in the 2030s, even when its power finally fades and its transmissions stop, Voyager will keep flying. 1 light day. Then 2. Then 10. Then 100. Forever outward, into the unknown.